Hello everyone, I am Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore. In this video, we are going to discuss about the example of approximation of derivative method and some more examples of Butterworth and Chebyshev filters. Here, convert the analog bandpass filter with system function h of s, which is equal to 1 by s plus 0.1 plus 9. Here, substitute s equal to 1 minus z by t into h of s, which gives h of z equal to 1 by 1 minus z by t plus 0.1 plus 9. Here, a transfer function h of z, which is equal to t square by 1 plus 0.2 t plus 9.01 t square divided by 1 minus 2 plus 1 minus 2 multiplied with 1 plus 0.1 t divided by 1 plus 0.t plus 9.01 t square z power minus 1 plus 1 by 1 plus 0.2 t plus 9.01 t square z power minus 2. If t equal to 0.1, the poles are located at p equal to 0.91 plus or minus j 0.27. C. The filter designed by impulse invariance. Remember, impulse invariance, it map a continuous time impulse response to discrete time, mapping a continuous frequency response to discrete time, which gives h of n, which is equal to tdhcntd. Here, h of e power j omega, which is equal to summation k equal to minus infinity to plus infinity, hc of j of omega by td plus j 2 pi k by td. Here, hc of e power j omega, hc of e power j omega, which is equal to hc of j capital omega, which is equal to 0 for omega less than or equal to pi by td. And h e power j omega, which is equal to hc of j omega by t for modulus omega less than or equal to pi. See the formula. Here, our first step is define specifications of filter, ripple in frequency bands, critical frequencies, pass band age, stop band age, and cutoff frequencies. Filter band type, low pass, high pass, band stop we have. And step 2, linear transform critical frequencies, omega equal to omega by td, replace with that. And step 3, select filter structure type and its order. And step 4 is convert h of s into h of z using linear transform and verify the result. It does not meet requirement, return the step 3. These are all the steps involved in impulse invariant algorithm. See the example. Convert the analog filter system into system function h of s equal to s plus 0.1 by s plus 0.1 whole square plus 9 into a digital IIR filter by means of impulse invariance. Here, it has 0 set s equal to minus 0.1 and pair of complex conjugate poles at minus 0.1 plus or minus j 3.0, and which gives the output h of z, which is equal to 1 by 2 divided by 1 minus e power minus 0.1 t e power j 3t z power minus 1 plus 1 by 2 divided by 1 minus e power minus 0.1 t multiplied with e power minus j 3t z power minus 1. See the frequency response of a digital filter and see the frequency response of analog filter. The frequency response of digital filter which meets the required condition when compared to analog filter. In filter design by bilinear transformation we have. Here we have to map the entries of S plan onto a unit circle in the Z plan, nonlinear transformation, frequency response subject to warping. Here in bilinear transformation, RS is equal to 2 divided by TD multiplied with 1 minus Z power minus 1 divided by 1 plus Z power minus 1. Again, the TD cancels out, so we can ignore it. So we can solve the transform for Z as Z equal to 1 plus TD by 2S divided by 1 minus TD by 2S, which gives S equal to sigma plus j omega, which maps the left half S plane into insides of the unit circle in Z, stable in one domain but stay in the other. See the bilinear transformation. On the unit circle, the transform becomes Z equal to e power j omega. To derive the relation between omega and omega, that is small omega into ohm, here it represents Omega, which represents a frequency, capital omega ohm symbol, which is equal to 2 pi EF here. C. Here the value of S, which is equal to 2 by TD 1 minus e power minus j omega divided by 1 plus e power minus j omega, which is equal to sigma plus j omega, which gives 2j by TD tan omega by 2, which yields omega equal to 2 by TD tan omega by 2 or omega equal to 2r tan omega TD by 2. See the output of bilinear transformation. See the output for omega p and omega s, pass band and stop band. See the output omega p, which is equal to 2 by TD tan omega p by 2, omega s, which is equal to 2 by TD tan omega s by 2. See the output omega equal to 2 by TD tan omega by 2. See the frequency response curve, which is mapped into frequency and magnitude, that is ohm omega and hc of j omega. See the mapping of bilinear transformation S plane into Z plane, S plane and Z plane. J omega S mapped in imaginary Z axis. See the real part conversion. And here the circle, unit circle is mentioned in +1 and -1. Here our S plane values are mapped into Z plane. See the frequency response mapping. And we have some more examples for bilinear transformation, impulse invariance method for designing IIR filters. We'll see the examples and problems in our next video lecture. Thank you. Thank you all. Thank you for watching.